Now, let's talk about well-behaved functions, because psi must be what we would call a well-behaved function. And so psi must be a normalized, well-behaved function. Okay? And why do we want it to be well-behaved, and what do we mean by well-behaved? Okay. We want it to be a normalized, well-behaved function because, remember, our interpretation is integral of psi star psi over all possible locations must be equal to 1. So when you see this symbol right here, integration, and your integration variable is tau, that simply means integrate over all possible locations. Okay? So the integral of psi star psi over all possible locations must be equal to 1 because that's our interpretation of psi squared. Integral of psi squared over all possible locations must be equal to 1 because it's a psi squared is a probability density function. So a well-behaved function is one that is single valued. What do we mean by single valued? For any given location, psi squared can only have one possible value. Why is that? Well, because we have to interpret as probability density, it must be unique. It has to have a unique value at a given location. What if I were to plot psi versus, let's say, x, and my psi looks like this? Well, at this location, I got 2 possible values of psi. Which one do you pick? So that's not acceptable. So that's a function that is not single valued. For a given x here, it has 2 possible values. Over here, it has 1, 2, 3 possible values. So it has to be single valued for it to be acceptable. Okay? Whatever psi is, it has to be single valued. It must have a continuous first derivative with respect to the coordinates. Okay? And the reason you want its first derivative to be continuous is so that the second derivative exists. Okay, if the first derivative is continuous, then you can take the second derivative of the function. Why do we want that? Because we are going to postulate, in another postulate, we're going to say that the way we solve for psi is to solve what's called the Schrodinger equation, which is a second-order differential equation. Okay, so we must be able to take the second derivative of psi. Okay. And that's just a postulate, because we're postulating that how we solve for psi is to solve what's called a second-order differential equation, and that requires us to take the second derivative of psi. So we want the second derivative to exist. All right. Now, finally, a well-behaved function is one that is normalizable, or what we would call quadratically integrable. Okay? What that means is, if you were to integrate, okay, the function over all possible space, then it should come up to a finite value. So it cannot approach infinity. Your psi cannot go to infinity. Its value cannot blow up, okay, in regions where your system can exist. Okay, you just cannot have an infinite probability of finding it at a particular location if it goes to infinity. Okay, so an exception will be an unbound system where your psi can be, we'll talk about that some other time, okay, where your psi can be, is not bound, so there's no restriction on where you can locate your particle, in which case it doesn't have to be normalizable or quadratically integrable. But it still cannot go to infinity. It can oscillate, okay, as you go to infinity, positive or negative infinity, but it cannot go to infinity itself, the function. So that's normalizable and quadratically integrable. By the way, this condition right here, okay, that this value is equal to 1 is called the normalization condition. Okay? So we say that the square of psi, if you integrate over all space, must be equal to 1 if we insist that that is a probability density function. So that's what we mean by quadratically integrable. Quadratic means what? Second power, right? So if you square it and then you integrate it, you should get a finite value for the function to be called well-behaved. for psi itself, okay, psi that integral must be equal to 1. Then you say the function is normalized.